Okay, so we have this next problem in our modern physics section, and it's dealing with an atom being split into two helium atoms, releasing an amount of energy, and then us finding the kinetic energies and the speed of the two atoms that were produced after the split. If you remember from your intro to physics class, maybe you dealt with collisions before, or explosions. An explosion is really a collision backwards. And this splitting of the atom we can think of as being like an explosion. So we're going to work with momentum. Now, what we want to do here is think about the momentum prior. So we have this atom. And then it splits into two separate atoms. And when it splits, it releases this energy, and the two atoms shoot off in whatever these directions they're going. Okay? So we have, what I'm going to use is the M in black, and then the two M's in red to represent the mass of the different atoms that we're dealing with. Now, if we think about our before picture, see if I can write that E a little better. What do we have? Well, our momentum is equal to big M times the velocity. And if we look at the after the explosion, our momentum is equal to mass times, we'll just call V1, plus mass times V2. Now, the important thing to know here is that the masses, both red masses are the same. They're both two helium atoms that are produced. They have the same mass. So I'm going to call those just red M. I use that in the colors so I can see. And the black M is the other mass. Cool. So we can set these equal to each other. We can say your momentum, let's actually try to be color coordinated here. Your momentum initial is equal to your momentum final. Or mass times velocity is equal to M times V1 plus M times V2. Now, if we look back at the problem, we see that our atom was at rest initially. So this whole section is just 0. We can divide out by the M's, and we see that V1 is equal to negative V2. So in other words, the speed that this atom is moving in this direction, the other one is moving in at the exact same speed, but just going in a different direction. Speed is the magnitude of velocity, and they both have the same magnitude, the same speed, but they're going off in opposite directions. So that's what this bit is showing us. Cool. Now we want to look at the kinetic energy. Kinetic energy. And we know, just as a reminder, the kinetic energy is equal to 1/2 mv squared. So the kinetic energy from the first, well, let's do this in red. Let's keep up the trend. Kinetic energy from the first atom that split is going to be equal to the kinetic energy of the second atom that split. Now, why is that? Well, we just have to look at how we define kinetic energy. Their masses are the same. They're both an helium atom. And we just found that the V squared, yes, V1 goes in the opposite direction, but when you square it, the negative doesn't matter anyways. If you were to plug a negative into here, you'll get a positive. So it might as well have just been V1 equals V2. So what I'm trying to say here is the kinetic energy from the first helium atom is going to be the exact same as the kinetic energy from the second atom. And I think that kind of makes sense. Now it mentions, if we go up to the top, that if you split into two atoms, it releases with this amount of energy. So what that's saying is, we'll use orange. We'll use red for the first bit. Kinetic energy 1 plus kinetic energy 2. So the kinetic energy between the two atoms that split is going to be equal to the 92.2. Let me write that 2 a little better. It's equal to the total amount of energy. Because if we think about it, the only type of kinetic energy we're getting is from the two helium atoms. We're not getting any kinetic energy initially because the atom's at rest. So this amount of energy has to be accumulated from the two kinetic energies. Well, kinetic energy 1 from the first atom is the same as the kinetic energy from the second one. So we could also say, let's let this be equal to just the kinetic energy total. Okay? Or we'll just say kinetic energy. So if that's the case, we have 2 times our kinetic energy is equal to 92. Oh, let me write that down. Let me change the colors. I'm trying to be somewhat organized here. So then all we have to do is divide by 2. And then finally we can see that your kinetic energy is equal to, and we're also going to go ahead and convert this here. I just want to try to stay times. Well, let's see. We have 10. 1 times 10 to the third all over 1. There we go. And this will drop with this, so our units make sense. Perfect. And if you plug this into your calculator, you should get about 7.38 times 10 to the negative 15 joules. Okay. So there we go. All done. Well, that was part A. Is there a part B? Oh, we have to find the speed now. Okay, well, that's all right. We have to find the speed of... Okay, they both have the same speed, so that's actually kind of nice. So the kinetic energy is equal to 1/2 mv squared. It doesn't really matter which one you're using because they all have the same. We can just say this is 1. But the mass and velocity is the same, so it doesn't really matter. And what we're trying to solve for is the velocity. So let's see. 2 times our kinetic energy, all divided by the mass, square root, is equal to our velocity. And we know the mass that was given in the problem, I believe. Yeah, we know the mass, and we just solved for the kinetic energy. So using from part A up here, part B is a breeze. All we have to do is a little bit of algebra and then plug in. And if you plug this in, you should get 1.49 times 10 to the 6 meters per second. And there you go. That's the speed. That's the speed of, I guess this would actually be velocity 1, right? Velocity 2 would be negative 1.49 times 10 to the 6 meters per second. It wasn't part of the question, but just so we see, because of what we found right here. They're the same speed, but the direction is opposite. So hopefully that makes sense and it helps you guys out.